And we're free falling. Looking back, Physics 30, we're looking at FM1.5, freely falling objects. So kind of twisting things 90 degrees, looking at dropping things. To understand how the use of the equations that we discussed in FM 1.3/1.4, can use that to discuss uniformly accelerated motion for free fall situations, so under the influence of gravity. And then solve free fall word problems involving the equations for uniformly accelerated motion. So one of the most common examples of uniformly accelerated motion is that of an object that's allowed to fall freely near the Earth's surface. Now, of course, the gravitational acceleration varies depending upon how high you are off the ground. So we're assuming that we're near the Earth's surface and that, for all intent and purpose, it is constant. That a falling body is accelerating may not be obvious at first. Near the surface of the Earth, all objects experience approximately the same acceleration due to gravity. This is one of the most common examples of motion with constant acceleration. Galileo claimed that in the absence of air resistance, because air resistance does play a part, especially if we're falling for some time, objects will fall with the same acceleration. So in this picture here, of course, the ball goes before the paper because we have air resistance here. But if we crumple that piece of paper so that I can minimize air resistance or have the same type of air resistance between the two objects, they fall at the same rate. This acceleration is referred to as the acceleration due to gravity, and near the Earth's surface we call the acceleration little g, and its value is 9.80 meters per second squared. And in fact, we'll be doing a lab here shortly after 1.6 in which we try to determine that value by doing a couple of experiments. Now, if we could have done this in a variety of ways. If I imagine the Earth, if I imagine putting something upwards in the air, I assume that's going to be the positive direction, so anything falling down towards the Earth is the negative direction. I could have used vice versa, it doesn't matter. So that's why I have that negative there. So something falling downwards, I assume to be a negative direction. Okay, so that's just to point that out. Of course, I could have had it the other way. It doesn't really matter as long as you realize what you're dealing with. It can be considered to be negative if the direction down towards the Earth is negative and upwards is positive. Actually, g varies slightly according to not only latitude and elevation of the Earth's surface, but these variations are so small that we ignore them for most purposes. The effects of air resistance are often small, and we will neglect them for the most part as well. However, air resistance will be noticeable even on a reasonably heavy object if the velocity becomes large. So, for example, that terminal or final velocity is reached. But we're doing short path situations, light objects for a short time in air, so we can assume the air resistance is negligible. When we do the next unit, FM2, when we're dealing with forces, then we'll kind of look at air resistance or drag, and we will factor that in. Acceleration due to gravity is a vector, of course. It has a size and a direction. And that direction is downwards towards the center of the Earth. So if we look at a couple of examples here, falling from a tower, suppose that a ball is dropped where VI is equal to 0. Initial velocity is 0. At a time of 0, how far will it have fallen after 1 second, 2 seconds, 3 seconds? Ignore your resistance. All right, we'll take a look at an example involving falling from a tower here. So VI is equal to 0. So we're looking at how far it went after these time periods. So if we take a look here, we know VI, it's simply 0. We don't know anything about VF. We have time. So if we look back at our equations, I believe it's this one. Delta D equals VI T plus 1/2 AT squared. Because we know we're looking for D, we know VI, we know the time period, and we know the acceleration. The acceleration is simply equal to little g, which is negative 9.80 meters per second squared. And the nice thing about that is that since VI, since we're dropping it from 0, this part of the equation basically disappears because we have VI equals 0 times t. Doesn't matter what t is, that part's going to be gone. So it's just simply 1/2 AT squared. So it's, and then a lot of the cases we have VI equaling 0, so that part of the equation we don't need. So let's take a look at, so maybe we'll break this down to 3 parts. At t equals, let's see here. So at t1 at 1 second, so the difference in time will be 0 and 1, so just 1. And then at t equals 2 seconds, and then maybe down here we'll do at t equals 3 seconds. Ooh, got a little funky there. So delta D equals 1/2 AT squared, because again, that first part is gone because VI is 0. So negative -9.0. From going from 0 to 1, of course, that gives us a delta T value of 1. And then, of course, don't forget bed mass. Exponents come before multiplying. Doesn't play a big part in this particular example, but negative 4.9 meters is what we get. Now, so and look at that. We have the answers here, hint, hint. We fall 4.9 meters. Now, the negative I have here just simply implying that we're going downwards. From 0 to 2 seconds, that's going to give me a delta T value of 2. So working that, 1/2 of negative 9.8, 2.0. And that's going to give us negative 19.6. And yes, it is. We have it right there. So that's quite a stretch. We went from 4.9 in the first seconds to negative 19. So you can see it's following kind of a parabolic pattern here. And then lastly, delta D, 1/2 A delta T squared. And you can see here the answer we should get is over here. So 1/2 of negative 9.8 after the 3rd second. Again, we're looking at from 0 to 3, so delta T is equal to 3. So yes, square that first to get 9, multiply by negative 9.8, multiply that by 1/2. And we get negative 44.1 meters per second. So you can see it's definitely a quadratic type pattern there. Because of that squaring factor, that times squared, that causes it to be a y equals x squared type scenario. Okay. Now we'll look at, okay, what if we had thrown it from the tower? So instead of having VI equals 0, let's say VI is equal to negative 3 meters per second. What would happen in that case? So what would be its position after 1 second and after 2 seconds? What would its velocity be after 1 and 2? And then compare that to what we would have had originally. So we have a little bit of room here. Try to write small. So I'll do the same thing here. And we can use the same formula, but that first part is not going to disappear though, because I have a VI value other than 0. So delta D is equal to, so after 1 second, now originally I'm being chucked down at negative 3. So at the end of 1 second is what I'm going to be calculating here. So be careful doing this. Bed mass, make sure you do the exponents before multiplying that out. Multiply this out, add it all up. I think when you do that, to save space, I'll kind of jump to the final answer. Negative 7.90 meters. So compared to being dropped, negative 4.9 meters, I've gone negative 7.9 meters. And of course, what if we're looking at from 0 to 2 seconds? What do we get in that case? So again, we're being chucked down at negative 3 meters per second. So from 0 to 2 seconds is what I'm figuring out here now. So what I get there as a final answer is negative 25.6 meters. So 25.6 meters negative, implying going downwards. Compare that to being dropped 19.6. Okay, what I'll do is I think I'll stop the video there. We'll finish off this example, do a couple of more, and then you'll be ready for the assignment.